seems to make a lot more noise than anything else. First of all, it's nice that I got 2 PhDs, but please understand that everything that we do now is basically disproving everything that I learned then. Okay? I mean, just between you, me, and the wall, I am what I am from all of the stuff that I've done and the science that I've made happen. So, don't read that one too strong. Now, Inteligentry Limited, anyways, that's a proper name. We are the research and design group that does all the research and design for an engine that we call the Plasmic Transition Process engine. Now, the Plasmic Transition Process engine is actually a expansion or evolution of something that happened in 1980s and 82 era that was done by a guy named Joseph Papp, who quite honestly had a lab experiment fail and tried to turn that into something, and basically did a good job of misleading half the world because he always thought it was something that it really wasn't. Anyway, we have taken this technology and we understand the process, we understand the science behind it, at least up to some point. Now, there are still equations that are giving us problems because we are still getting more power back or think that we should, the equations that relate to it. So it's not pure science yet. We do have nuclear physicists and students who are working with us and with the technology in order to get the proper scientific papers compiled, written, and sooner or later published. So it is not at this moment pure science, but it works. Okay. Now, in 1982, I go through the history of the Papp engine, but just between you, me, and the wall, it's really boring, and it's all convoluted with strange people and other people that have scammed and all kinds of shit. So it's really not worth the conversation. In 2007, I did the controller that was, I designed the controller that was programmed by my brother and his technician that made Papp's 1982 engine run. And we've got video of that engine running. That's the same engine that got certified at the University of Western Oklahoma. Now, that's nice, but just between you and I, it doesn't mean anything, because this engine ran, then they sent it down to Oklahoma, and the professors at Oklahoma couldn't get it started until Joe Papp flew to Oklahoma and made it run for them. And in my view, I've spent my life developing new products for companies. New products for companies mean that you have to have something you can replicate and the company can sell and make money. And in my view, the simple fact that Papp had to go to Oklahoma to make the engine run means that it was not that. It was not something that anyone could make. And as a matter of fact, in the last 30 years, that particular engine and any copies of that engine still haven't run. So that gives you some idea what can happen if you see something that's just simply a test and it's a one-man, one-up thing. And of course, we are trying to make sure we don't do that. When I discovered the process of how this engine worked, I actually had some of my friends check it, and it was kind of funny because I sent out these things to my friends in the nuclear business, and they sent me back a letter saying, oh, look, don't play with the PAP thing, it's a scam. But I sent them back letters saying, look, okay, I think this is how it works. Can you look at it? And the next thing I got was about 3 days of silence, and then after that I started getting back mathematic simulations from people going, well, you know what? This does look like it'll work. You're convoluting 3 different technologies in the nuclear field, but they will work together this way. And so things kept going that way until we finally realized that we had found the specific process that actually does make this engine function. And of course, that's when I filed for a provisional patent. That patent is now a true patent in that it has been published. We do have a number, and we're just simply now waiting for the letter to come from the patent office to give us permission to go on with it. So we do have a patent on this process technology. Also, because my background is mostly electronics and embedded electronics or laptops or computers or mainframes or whatever, okay, I understood early on that the control of the engine was the single problem that's held everybody up. Because the engine, if it's not precisely controlled, won't function, period. Or it'll blow up. Either way, not a good thing. Okay, so our patent is basically on the process and the control of the engine. The instance that we used in the patent is basically the public domain engine. Now, PAP's patent went out of patent in 2003. So anything that's gone on with that engine is public domain. Any one of you here can make one if you want. And as a matter of fact, here's a copy of the engine that was in that patent. Now, I want you to understand that this is not an engine. If you look at this very closely, what you'll find is it's a head replacement on somebody else's block. You'll notice there are pistons at the bottom that go into the crankshaft, etc. The actual mechanism itself that does anything is from the piston, or from the head, basically, up. So it's a kind of a misnomer to call this an engine. The 1982 engine was developed by PAP International and was actually machined by the family machine company before it went broke. And it was not in 2 pieces, but a single piece. But it was still the same technology. And so that's how that technology sits to this day. In this technology, you'll see that the pistons are actually the cylinders are actually upside down. And they actually come down and go back up, and you've got these long things. And, oh, I'm supposed to use this thing, probably. Anyway, right here and right there are 2 nodes inside the cylinder, and they're both radioactive. Okay? And that's how they accelerated the electronic arc that actually ran through them. Okay? If you watch any of PAP's information or read any PAP's information, he tells you about all the positronics, X-rays, camera, you name it. I can't find anybody in the nuclear physics world that says that's even possible there, particularly. Okay, it's all pretty much hokey pokey. So, but this did work. Okay, that was the key, that it did work. Okay, so now we went from that engine and that technology over to our own, and here's our technology. Now, as you can probably tell, this is a little simpler. This engine has 5 moving parts. Okay, it doesn't have any nuclear nodes, and it doesn't have any of the rest of the things that you don't need to make this process work. The process that the engine uses to make things happen is that it creates a pseudo plasma. Now, in 2.5 years, I've been saying it creates a plasma. Well, my physicist jumped all over me about a week ago and told me that I had to quit saying that because we do not create a plasma. Creating a plasma means you create a plasma and maintain it. Well, if we did that, the piston would come down and never go anywhere else. Because if the plasma is filling up the chamber, it can't go anywhere. So we do instead is, they said to say that what we do is we make a pseudo plasma. We actually generate a plasma long enough to take up the space, and then we take away the electronics that actually wants to make that plasma happen. And we let it then collapse back to a steady state. And a steady state in this case is a gas. Now, the easiest possible way to understand how this engine works is, those of you who have ever seen a steam engine, is a steam engine. In a steam engine, you got a cylinder sitting here, and you put in hot water, and when it hits the non-pressure, it turns into steam. And the steam then fills up the chamber, moves the piston. Well, basically, we do the same thing. The pressure in the cylinder, or in the closed chamber itself, is 1 atmosphere. And that particular gas now is static at that point. What we do is we ionize or invigorate the gas up to a point where it wants to be something else, in this case a plasma. And then we apply the key element, which is an activation, a ball lightning kind of activation, okay, which then creates or coerces the gas to change from a gas to a plasma. And that expands, builds up the chamber, and the piston moves, just like the steam engine did. And then once it gets to a certain point, we turn it off, and it collapses, just like the steam engine does when the steam turns back into water. Now that's the easiest possible way to understand how this works. It's simply an expansion. Now, we're all used to our internal combustion engines. The internal combustion engines work off of an explosion. That means that when the spark plug goes off, there's an explosion that releases a lot of energy for a very short time, which drives the piston down, and then the remainder of the cycle on that is handled by kinetic energy in the flywheel or wherever it's stored. Okay, well, in this case, it's like blowing up a balloon and then letting the air out. Then blowing up a balloon, letting the air out. Blowing up a balloon, letting the air out. This works by way of expansion. There's no explosion in this cylinder. There's simply an expansion. So, we control all of that by way of electronics that are handling how it functions. Okay? Now, so that gives you an idea of what our engines pretty much look like, although this is a real drawing of it here. Okay? Can we, yeah. Do I have to push? Can you push that? I'll get into that here in a sec. Yeah, no? Okay. Now, this controller doesn't handle this. It only handles. Anyway, this is This is a 2D drawing of what we're actually in the process of manufacturing right now. Right this second, we are creating 5 what we call training engines. These are 5 engines that are being manufactured using numerical control techniques, not hand machined, but production machined. And these engines will be used in our training courses as we license the technology to others, or as Plasmic licenses the technology to others. This particular engine, okay, like I said, is interesting from the standpoint that it will be mass produced. And also, once we get the first of these training engines operational, is the last time we'll be asking anybody for a dime, because then we'll be able to license. And the reason for that is because I'm kind of hard-nosed. I don't believe in taking somebody's money to license unless I can give them something that they can learn. And the only way to give them something that is real to learn is to make sure that they can build an engine from parts that are made on production equipment and make that engine run and then take it home with them. Because to me, until that engine works, we don't really have a product, we just have test engines. Okay? Now, let's go back to the other thing. The engine is kind of interesting from the standpoint that, oh, do I do this now? Okay. I said that the engine must be precisely controlled. In order to be safe, the engine has to be very precisely controlled. The engine changes speeds by using a virtual cylinder. A virtual cylinder means that there's an electromagnetic field that's being produced in order to channel the plasma into an ever smaller cylinder, but the cylinder gets longer because the volume of the cylinder is still the same, but now you're going to cut it off faster in order but your time to fill is still constant. So this is the controller that we actually use in the engine. There's a block diagram of the entire controller. Now, early on, that controller was done on one board about that big. Okay, on the first test engines with a pretty good sized board. On our current test engines, it's boards like this. Okay? This board does everything that the engine requires in order to run. Okay? And it does it in a way that it controls the engine that it watches. In other words, this controller is hooked up to sensors on the engine that tell it exactly how things are working. And if something goes amiss, it shuts it off. Okay. But that's a block diagram. It gives us some idea of the complexity of the control system itself. The control system is really much more complex than the hardware. The hardware is really quite simple. Now, in order to actuate a gas and convert it over to a plasma, it takes about 140,000 volts of electricity in order to fuse 2 atoms of helium. Now, the gas mixture in this engine is pretty simple. It's helium, neon, xenon, krypton. What did I miss? Okay, argon. Okay. I'm sorry, but, you know. Anyway, it's a pretty simple mixture, and quite honestly, the 100 cc cylinder of the engine, okay, and this particular mixture does a 5-to-1 expansion. That means that starting with 100 cc's, when you convert it to a plasma, it creates 500 cc's. Okay? And you don't have to pulse it. You don't have to do anything with it. All you have to do is set up the ionization factors and start it. It will complete that function on its own until you take off the ionization and the control functions that create that, at which time it will immediately decay back to a gas. Now, there's a lot of misunderstanding for how a plasma that's being used like we do actually functions. So let me explain how a plasma works. When we create a plasma, the plasma actually produces some heat as it expands. But when we take off the electronics and allow it to go back to being a gas again, go back to steady state, during that time it creates a vacuum because it's 500 cc's and it goes back to 100. And the other thing it produces is a negative thermal event. Okay? There are people running around going, well, the engine can't work because the thermodynamics are wrong. And the only problem they have is that they don't seem to understand that when a plasma turns back into a gas, it has a negative thermal event, not a positive one. So they end up canceling each other. That's why this engine doesn't produce any heat, because there's nothing left there to produce. Okay? The actuator of the system is actually a fusion of the helium atoms. Now, that fusion creates an enormous amount of heat, 5 times the temperature of the sun. It also produces about as much energy as a 5-gallon tank of gasoline. The only real problem with that is that it does it for less than a billionth of a second. Well, a billionth of a second is too short for any memory to remember, for any metal to remember. So the metal doesn't pick up any memory of that heat. So you'll notice that when we get into the horsepower charts, we've got a line at 2,800 RPM. And the reason for that is that theoretically, and no, we haven't tried broaching this yet, but theoretically, the repetition rate of the creation of the plasma and the degradation of the plasma and the actuation event at 2,900 RPM could start to cause some heat memory in the metal. Well, now that said, we got the other side of the coin. There's always something on the other side, right? And that is that when we made that computation, we were using all metal components. The piston was metal, everything was metal. Okay? Well, since then we've evolved rather radically. Okay, we've gone from basically steel cylinders over to non-magnetic stainless steel cylinders. And the pistons have gone from all aluminum, okay, this was all one big aluminum piece, to what we use now, which is this kind of arrangement, where the head of the piston is aluminum, but the back side of the piston is a high temperature, high strength plastic, thermoplastic. And quite honestly, it makes a better piston, okay? As a matter of fact, in the production engines that we're doing, we're only actually using 1 ring, not 2. But this gives us a much different thermal footprint than what we originally put into the numbers to start with, but we really haven't had time to try and go back and make all those things happen. And nobody's complaining because we only turned 3,000 RPM, or 2,800. Now, here's something interesting. This is the next piston that we're going to test, right here. And this is the next head that we're going to test. Notice, neither one of them is metal. Okay? These are both high temperature, high strength plastic materials. Okay? Oh, thanks. You could hear me getting that way. Okay, good. Anyway, now, what we found out was, now when we first started working with this, we were concerned because in the original running videos of the tap engine, okay, the thing looks like it's doing some nasty stuff. What we didn't realize was that the process they were using was so inefficient that what we were seeing were really ionic side effects, or they're actually creating duonium as a side product. And so we didn't think that plastic would work. And quite honestly, just between us, until about a year ago, these plastics didn't exist. These are now, like I said, available and quite easy to use. And as a matter of fact, we found out about this plastic from a company in England that is actually running or testing Formula One engines with these as pistons. Okay?
What's the name of the plastic?
Huh?
What is the name of the plastic?
I'll tell you the truth, okay? If you give me an email, I'll get you the name of it. It's not Peak, it's on the other side of Peak. I don't remember off the top of my head, really. I've got a couple of mechanical engineers to take care of that stuff. So, but anyway, I can get it for you if you just send me a message. Okay. Now, remember I said that in the PAP engine they had these two nuclear nodes, and they ran this arc across it, and that's how they got it to go. Well, I didn't like having two nuclear nodes in there when I couldn't find a good reason for them, and none of my friends who are physicists could either. So we devised an entirely different triggering plan. And in our triggering plan, now, the first triggering plan we used worked, but it would require a metal piston because we were firing across the piston. Okay, in the system now, you've got 4 electrodes sitting here, and that center one there is a strontium bar. Okay? Now the reason for the strontium bar sit there is that the strontium bar has an impedance that is slightly above the ground. And so what happens is we feed 107 kV into each one of these, and it jumps over to that strontium bar, and because the strontium bar's impedance and the fact that it's flat, it creates a little ball of lightning right on the end. And it creates a ball at 400,000 volts. Okay? Remember I said it takes at least 150,000 to get a fusion. And the fusion is the key to the access. Okay, so that's what you're seeing there. And to give you some idea, this is the real head. Okay? This one has been used. All right, you can see here, there's the 4 electrodes. Okay, this is the radio frequency injection. We probably didn't talk about that, but in order to ionize the gas, we use electromagnetics to squeeze it, and then we add a radio frequency to just jiggle the hell out of it. I suppose that's as good a way to talk about it as any, because it really doesn't do anything except make them all get weird. And then on this particular head, you'll also see that there's a optical port here. Now, an optical port looks right exactly at this center line, so that we can see when the engine's running, okay, what is happening at that point, because that is the critical point. That's where the actual process starts every time. And we can tell from that color, okay, exactly what the process is doing, proper or not, okay? So, that gives us some idea how that works. And that's basically all that was for. Now, someone asked earlier, what about RPMs? Okay. This engine is very strange to most of you who have internal combustion engines in your blood, because it does several things wrong. Aha! The man found out I had a bad back. This is good. Anyway, hope you guys don't mind, but I've got a busted back and I don't stand well sometimes. This engine is strange to the internal combustion people because, one, it doesn't care whether it runs clockwise or counterclockwise. It's two-stroke. That means if one stroke is power, and I imagine you all probably figured this out, but one stroke is power and the other stroke is return. Okay, there's no other strokes in the engine. It's completely sealed, which means it doesn't breathe air, doesn't make air, doesn't put out any kind of carbon, and because of other things, it's just absolutely, marvelously good about things. But the other thing that it will do is it will run at very low RPMs. As a matter of fact, we tell people not to go, we tell our people not to go under 100, but we've actually collected data at 10. So this is a horsepower chart based on different engine sizes, different numbers of cylinders, different displacements, and in several cases, different mixes of gas, of fuel. The engine is also scalable to some degree. That means that because of the way the actuation system works, we can come down to 250 cylinders and a single electrode. Okay, but probably going under 250 cc's is going to take some further research, because you're now into the realm of being almost entirely too small for it to function properly. So it'll make a hell of a lawnmower, but you're not going to get it really, really small. But just looking at.
Mind if I ask you, I know you're so into the details of what you're doing, could you say what your engine does and then what kind of fuel it puts out and the details
Oh,
of what it actually does?
well, it's a reciprocating engine, two-stroke. It uses for fuel 5 gases that basically cost about 31 cents a chamber to put in. That particular engine, fueled, running, if I put it in your car, will allow you to drive over 144,000 miles nonstop. That means you don't have to refuel it for that long, right? And these are the horsepower charts that the engine would produce for power at given rates. We specify the engine basically up to 2,800, and we tell people not to go, well, we will be telling people not to go higher than that. Okay. So, huh?
What kind of energy are you putting in, the electrical energy?
Well, it depends. Okay, and let me get into that later on, but his question was, how much energy are you putting in? Well, We use a virtual chamber, okay, in the engine in order to get speed. The virtual chamber requires more voltage and current as the speed of the engine comes up. So at 2,800 RPM, I can give you this number, at 2,800 RPM, okay, the voltage onto the cylinder coil, that's this one, okay, the voltage onto this coil, which sets the virtual cylinder size, is 48 volts at 2 amps. Okay? The rest of the electronics actually stays pretty much constant at about 12 volts and 6 amps. So that will give you some general idea what the pretty typical power requirements input are. Okay, now, and
Does the gas
you,
break down during use, or is it continually recycled?
well, okay, there's a lot of parts of that we can get into here later, but does the gas break down? Well, theoretically, okay, theoretically, because we're going, and this is based on the calculations we made on the original engine, not on the new ones, okay, that breakdown would happen at about 4 months, okay? However, that engine was about 30% as efficient as the modern design, the new design. The new design actually, the controller that handles the actuator watches the cylinder, and when the event happens, okay, there's a spike, okay? When that high voltage controller sees that spike, it shuts off. The reason it does that is because we don't need to burn more than one set of atoms in order to get the actuation, one pair. And so because the controller turns off when it sees this spike, okay, it doesn't continue to generate high voltage and use that current, and it doesn't continue to create high voltage and burn up more of the nuclear part of the hydrogen or helium fuel. Okay. Also, there are other things that we've done to the engine that make it even more efficient. You'll notice that the piston and the head both have what look like funny surfaces. Okay? Well, I understand a good deal of this is in provisional patents right now. But you notice that this is a donut, but it's not exactly round. Okay? And this one has exactly the same contour. And the difference is that this surface right here is parabolic. Okay? The focal point from this is right here. And the focal point from that one is right here. And the reason that we did that was we found out that we could get a lot more efficiency by redirecting the flow of the expansion so that it became linear. You're starting to understand how far we've gone with this now. Okay. All right. So we have been evolving from that very first test engine through steps as we go that have made the engine more efficient and more efficient and more efficient. Also, the electronics have evolved. In other words, we started by using good old-fashioned car coils. And what we ended up with doing was, I'm sure any of you that have worked on your car have probably seen one of these. This is what's called a COP, coil on plug. Okay, this thing normally plugs into your spark plug on your car like that, okay, and runs your spark plug. Well, we needed high voltage and we were using plain old everyday. Well, actually we started out with capacitive discharge systems in order to get power. And then we changed over to COPs, and then we found out that even though Granatelli tells you that one of these is good for 95 kV, they lie like a sieve. This thing might make 63 if it's lucky, right? And then we went looking for, gee, who makes these? And we found a company, and they make them for NASCAR, okay? And we said to them, we need 100 kV. And they said, well, the best we can do is 95. And we said, fine, we'll try it, right? I mean, after all, if it does 95 on 12 volts, what's it going to do on 17? So it turns out that we use these then as our primary source, and by going to the 4 poles, we get to 400 kV. Now, to give you some idea of the evolution of that, okay, in the first and second group of engines, we actually took a spark plug for an electrode, because after all, what's simpler than a spark plug for an electrode? Well, you could run a copper wire, and we found out in a hurry that that's really a lot more trouble than you think, because the copper wire wants to talk to the aluminum, right? But these guys don't talk through the ceramic. But so what we did, we took this piece here off, and we started putting them in, which you'll see on these heads here, with a holder that holds them in there, right? Well, then we got talking to the people who made our coils, and they came up with a new wind design for the ferrite, and these new coils produce 114 kV, and these aren't, this isn't them, but the new coils are only this big, okay? And they also came up with a new iridium spark plug, okay? And, oh, I brought the wrong one. Anyway, it's got a much longer tip on it, and so we actually cut them off a little bit like this, so we can screw them in now. Now, that makes up the electrodes for the head. It's about as simple as you can get, and does everything you need to do. Now, when the production engines get ready to go, this company is going to come in, have a look at that whole section, and because they understand how many engines are going to be built, they are going to make a single piece that can be threaded in there, so that we won't be doing spark plugs and plugging all that. Okay, and when they do that, we've got a new version of the actuator system that is being done in surface mount, and it will actually be internal to that unit. Well, actually, it's a slide-in card. So that means that the electronics that makes the engine work will become simpler. Now, that's good if you're going to manufacture, okay? But other than that, it probably doesn't make a lot of difference to most of you. But it does give you some general idea how fast the evolution on this happens once you find out that you were right and you start trying new things and breaking into new areas. This particular engine is the 5th generation of designs that we are looking at and testing. Now,
So is it a continuous series of plasma blasts that you're sending in there? Or is it just one and then it keeps going?
no, the plasma is created one time, once, because it's dumb to do it more than that.
Okay, well, it's a,
No, well, as long as you leave the excitement part on the gas, okay, once it's started, it will automatically continue, okay, because it started, okay? You don't pulse anything. You got to understand that there's people who say, well, you got to pulse it. The problem you got is that in order to pulse it, you would have to turn it off, wait for it to reionize, and turn it back on. Because if the gas is not ionized, if the gas is ionized, it won't go back to a gas state. And if the gas is not ionized, you can't make it turn into a plasma. So you can't, there's just no time to do more than one pulse. And every time you do that pulse, you're going to burn up part of your helium environment. Which means that all you're going to do is give your runtime, start bringing runtime. We have worked to make the runtime on the engine the very longest we can. And quite honestly, and I'll tell you this quite honestly, we really don't know what that is. We know from calculations on the old engine, it should be 4 months.
So you fire it up and you leave it running, and it's just always going to be running. You never shut it off like a car. It's gonna be-
Oh, you can turn it off. I mean, when you turn off the engine, you can turn it off.
Hold your questions until the end. That way we can get them all on your mic and
Huh?
all on tape.
Well,
Thank you guys. Thanks for the meeting.
anyway, go ahead. Anyway, anyway, that's a horsepower chart, and this is actually taken from measurements and what you see up there is pretty straightforward. You can see that out of a 1 liter engine with 2 cylinders at 1800 RPM, you've got 274 horsepower. Now, I'm being told I got 15 minutes, so I guess I better hurry. Next thing I was going to tell everybody about is this is a little unit that we use to test fuel expansion and to test different coils. Okay? What we do here is we try different fuel mixes to see how far the piston will move given that fuel mix. Because depending on the application, you may want it to move a certain amount and not further or whatever. And we also put this together so we could test coils. And don't worry, I understood your hand. We'll get to it here in a minute. Okay. But anyway, this unit has been used for some time to test. Okay? As a matter of fact, one of our stockholders actually made this. Now, we decided one time, and God knows why it took us, months to do it, but we just happened to be looking through past patent, and we realized that we knew what his coils were wound like from the description. So we wound a coil to PAP's original specification. And we stuck it in there just to see how it would fare out with the rest of the stuff. Well, we expected the piston to move 5-to-1 like everybody else. But the piston went, it moved that far. It did nothing. I mean, virtually nothing outside of glow. And then, after it got done, we thought, well, something we did wrong. So Mike to move the coil so we could see what was going on. And when he touched the coil, he pulled back his hand in big time and said, "Man, that's hot." Turns out, and we didn't know at the time until we went and got a heat gun, the coil was sitting there at 204 degrees. Now, in this particular unit, if you look at the far left-hand side in the back there, you'll see a little blue thing. That's a balloon. When we charge this system, we overcharge the system and we put up some fuel in the balloon, just to make sure that we got the chamber filled. Okay, because like I said, it's not meant to be anything specific other than how far does piston move. And that's a bed spring. Now, what's interesting is that when we move the coil from the chamber over the bed spring, the temperature on the coil goes up. And it will stay that way until it creates a vacuum inside the chamber. In other words, it will physically suck the balloon back into the hole. Now, this is an anomaly. This is not something that anybody that we know about has ever seen before, and we have repeated it several times. And so all of a sudden we lost a test unit because we are being asked by several colleges throughout the world and the country to not touch it. They want to come and study it. There's a couple of other things you should know about this. If we put this thing in a light-proof box, there's absolutely no video being emitted. If we look at the infrared, we find the heat from the coil, but only from the coil, nothing in the cylinder. If we put it in ultraviolet, we see absolutely nothing. If we put a radio frequency spectrometer in there, okay, we get nothing. No radio frequency being generated at all. And you can take this coil and physically hook it to the ground, and it still stays hot. Now, what's truly interesting about this anomaly is that is a plastic high-temperature vinyl clear tube. The coil goes up to 220 degrees, but nothing happens to the tube, nothing happens to the bed spring inside, nothing happens to anything but the coil. So I'm trying to explain that this is an anomaly that no one seems to understand at the moment, and that, like any other good discovery, it was something that failed and did something and went, oh, okay. But I thought I'd show you what this unit looks like, because in case you do see something come out here, and from different physics, we got our physicists, you'll find that they may mention this, and we have a whole group of people coming by to take a look at it. Okay? Now, well, that does that for that. Okay. There's a whole lot of other stuff, videos and all kinds of other things that we have, and unfortunately I'm being told I'm pretty much out of time, so if you come by the booth, bring a flash drive and we'll give you any kind of thing you'd like to know, and we'll tell you anything you want to know. We hope to have the production version of the engine ready in about 6 or 8 weeks, and at that time we will start licensing manufacturers, and as soon as they have shelf stock, we plan to go public. Okay? It is our philosophy and my philosophy that until you have something that you can produce and that you can sell to an end user, you don't have a product. And so it's our philosophy that we will not be showing any of our test engines running, because they are test engines. They are hand-built, one-of-a-kind engines that were, in some cases, testing one thing, one part of another part. They are collecting data for us, but we're not using them for anything to get people in any big hurry. We want to go public when you can physically go and buy an engine and use it for something. And so we're going to wait until our manufacturers have shelf stock, and then we're going to go public with the engine in boats. It looks like boats, aircraft, and personal power to start with, and water pumps or fluid pumps. Okay? But just so you understand the philosophy.
Are you up for questions?
Say again?
Are you up to questions now?
Okay.
How,
When it comes time
Actually,
to
this
questions and
poor
answers,
man here needs to ask me a question first, but go ahead.
John, are you ready to take question and answers?
Huh?
When it comes time to question and answers, I was going to do the
You
usual
said
protocol.
I'm down to 5 minutes.
Well, whenever you're ready to start taking questions, then we'll let our moderator here hold the mic, and they can come up, and that way we'll have them on the. You ready?
I don't care.
Okay.
I don't know, I mean, there's,
Who has a
the
question?
thing is, we've gone so far with this technology and changed so many things that it's really kind of hard to put it into anything that makes a lot of sense unless you're sitting there looking at it. And all the videos and everything that I brought don't seem to fit his player.
We have that one, do you want it?
Huh?
We do have that one.
Well, we got the one, go ahead and put it up. All of our mechanical engineering on this engine is being done by a product called Inventor. It's a 3D drafting process for mechanical engineering. And I gotta tell you that it is the most impressive damn thing I've ever been around in my life, because you don't have to go to a machine shop and make parts. You can make the whole engine, put it together, run it, and see if it's going to conflict or whatever it's going to do, and then just kick back and relax and watch it go. And then you turn around and you have a 3D printer, another very interesting thing in today's world, crank out the parts so you can go have them cast. Really nice the way the world is now. Okay, anyway.
You're hot on the screen.
Hmm?
You're hot up on the screen.
Yeah. This is an animation done from our 3D process. Now, if you're wondering, okay, the jagged edges out there are actually 36 teeth that runs under a sensor with the 36th tooth missing. And from that, we generate a signal that is given back to the master processor, so it knows where it is in the rotation, and it knows where it is to within half a degree. So, okay.
Okay. My name is Harvey Fiala. I'm a graduate engineer from California Institute of Technology. I've been going to these conferences for 10 or more years, and the title of your talk, Understanding Plasmic Transition Process, didn't give us a clue that it's about the PAP noble gas engine. See, and there's
It's got nothing to do with the noble gas engine.
nothing.
Nothing.
Well, see, there's an article in Tesla Tech journal maybe
Okay.
5 or 10 years ago, and it mentioned that an engine, said that no
Yeah.
one understood it yet.
Yeah.
And it mentioned there was a
We
engine that
started-
was demonstrated in LA and it exploded. Now, I'm
Well-
guessing that you finally understand it now.
Well, okay. The process that the PAP engine uses creates a plasma, and the plasma reverts back to a gas. From that standpoint, that's as close as we get. Okay? The rest of what PAP had to say about that, basically in his patents, and even in public, okay, was basically hooey. He did a great job of telling people that the gas was magic, and that held up people for 30 years. Okay, he did a great job of trying to explain things in ways that didn't make good sense to even scientists at the time. And don't get me wrong, okay, I think Feynman was dead wrong. The scientific mind does not go to look at something new closed, and he did.
Yeah,
So I don't
was-
consider what he did as right or wrong. And had he done it any other way, we wouldn't be here today, we'd be using this engine, okay?
Right, Feynman was my instructor, and I'm not defending PAP, but...
Oh, no.
But I thought, gee, it's a shame that there's something there, no one understands it, and finally, the good news is that some people like you took that basic process and figured it out and are exploiting it now. That's
Right.
the good news.
Well, two things bad happened, okay? One is PAP's engine, after it was certified, went back to his home, and when he died, the IRS took it. And because of that, the controller that we had on that engine went there as well, okay? And at that point, CEI and the rest of those people, Klosterman, that group, okay, decided that they would create their own controller, and they did so with a bunch of relays. But they did it without looking at what the other controller did and how it controlled the process. And basically, they cut their own throat. I hate to put it that way, but,
I understand.
okay. Well, okay.
Thank you.
And that was one of their mistakes. So yes, we started by looking at that process, okay? And then we found out that basically everything that was written, or, I mean, even the patent is pure legalese and patentese. It's, you know, so yeah, we started with that, but quite honestly, we learned early on. Remember I said that inside the head, we thought there was a lot of residue, right? Well, the problem, and this slowed us down early on because we expected a lot of heat or something. It turns out that the way PAP triggered it created monstrous amounts of collisions and a lot of ionic changes. And a good deal of these are what you were looking at. They were dark brown colored, and you know, it made you think that it was burning something. And then, of course, you sit down and go, what the hell was it burning? Right? I mean, these are gases that don't normally burn. And what was really happening is that his particular triggering system, or actuation system, was actually not just fusing the helium, it was fusing neon on the other side, which no one would have expected, okay, but would have produced that particular ion. So we have come a very long way.
Is Pat still alive?
Oh no, Pap died in 1989 or 1999, so I don't know, sometime in there. Okay, he died and Sabori's dead. Actually, if you want to see something about the PAP engine, okay, the best possible stuff to look at is look at Sabori's videos. Okay, he does a much better job of presenting the system than PAP did.
This is a classic example of a phenomena which Pat didn't understand, but,
Well, of course he didn't.
and finally you guys have understood it, and
Okay, let's keep the questions on the mic.
Right. Anyway,
We have
go
one
ahead.
more here.
Fire away.
Hello, and thank you. I appreciate what you're doing. My gift, I'm an inventor, I've got patents, I've got ideas and galore. And this is probably the most spectacular thing I've ever seen. If there's anything I can do to help, I'm available.
Good.
So,
Send me an email and tell me that.
okay?
Intelligentry is a company whose charge is to go out and find people who have been scientists, engineers, etc., people who have been retired that shouldn't have been. Okay? In other words, just because you hit 65 or 60 doesn't mean your brain quit. But a lot of companies can hire 3 kids for what they're paying you, and so what they do is they retire you. So I formed Intelligentry because I wanted to put together a brain trust of people who were retired, experienced people, so that we could open up the doors, because we're supplying the engine to Plasmic, and they're going to be doing the licensing and stuff, we will have a revenue stream from that. And I want to use Intelligentry to just simply open up the doors to anybody who's got an idea that would like to come in, pitch it, and see if we can help them make it real. Okay? And give them a little bit of business help and that kind of thing, and just basically have some place to incubate some of what's going wrong right now. I mean, right now, there are lots of good ideas and absolutely no money. And even worse than that is there's no experience to help them, because the experienced people are dying trying to, find some way to go out and fish another day. Okay?
Come and talk to you.
Good. I can use it. We actually already have 3 people coming in next month with ideas to present to us. So that is Intelligentry's charge. We're research and design. Go.
Okay, well, thank you, and I'm looking forward to
Yes,
how
sir,
we
me too.
connect.
Thank you, sir.
That was it. Ladies and gentlemen, John Rohner, thank you.